This is problem B about the Earth's rotation. And notice my little box, the way I set it up here, is already according to the kind of problem that I have at hand here in our book. All the problems are listed under a certain section, and then I just go in here in the summary, respectively in the chapter itself, and figure out what kind of equation do I probably have to use, and that's the way I set this up here. Anyway, so let me read it. Whoops. I'll change the color here. It says the Earth has a radius of 6,380,000 meters and turns on its axis once every 23.9 hours. What is the tangential speed in meters per second of a person living in Ecuador, a country that lies on the equator? At what latitude, that means the angle theta in the drawing, is the tangential speed 1/3 that of a person living in Ecuador? So let's just do one part at a time. So part A would be trying to figure out what is the tangential speed. So there we go. Person living in Ecuador, and therefore we know what the radius is. There we go. Country that lies on the equator. Yeah. Okay. Well, we have one of these three pieces, and by the way, they go together as tangential speed equals radius times omega. We're supposed to figure that out. We know what the radius is, but we don't know what omega is. However, if we use a second equation that says omega equals the change in angle divided by the change in time, and do we know that? Well, they give us a time. They say that the Earth rotates in 23.9 hours. And when it rotates once, we know that this one here is 2 pi. Because that's one full rotation. So that's kind of implied information. They don't say that straight out, but it's implied, and we would have to look out for that, that we discover that one rotation means 2 pi, and then the time it takes to rotate once is 23.9 hours. By the way, that's the same time it takes here as well as it takes here. It's just that here it's a smaller circle. Okay, I should say something about the 23.9 hours. Why is it not 24 hours? Well, the Earth rotates on its axis in 23.9 hours. 23 hours, 56 minutes. But at the same time, during that amount of time, it also orbits the Sun, and so the Sun is in a slightly different place. It's about 1 degree off, because it's only approximately 1 day. And because it's a slightly different place, the Earth needs to rotate a little bit further on top of the 2 pi or 360 degrees, 1 extra degree, and that is about 4 minutes that the Earth needs to rotate more in order to make exactly 1 day, the 24 hours. So in the 24 hours it actually rotates 361 degrees, but again, that extra 1 degree is to make up for that the Earth is also orbiting the Sun at the same time. So in any case, so we have 2 pi divided by, let's see, 23.9 hours times 60 minutes times 60 seconds, because we have to have it in standard units, so it's 86,040 seconds. And when we calculate that out, it's 2 pi divided by that, 7.3 times 10 to the negative 5 radians per second. And now we also have omega just calculated. Whoops. And therefore, for Vt, the tangential speed is what they want to know. We have a radius that is given, and we have omega. And now I'm going to move this down because I do need the space. And therefore we can figure out what the tangential speed is in meters per second. Okay, then in part B, what they're saying is figure out what the radius is at a different latitude where you have a third of the tangential. Let's see, was it the tangential speed? Yeah, I think that's what it said. Hold on. At what latitude is the tangential speed 1/3 that of a person living in Ecuador? So for part B, I would say RB, same equation then, where we have the tangential speed that we calculated earlier, but 1/3 of it, and we divide that by omega, and that is the same omega that we calculated over here, because the angular velocity is the same for both latitudes, because the Earth overall is a solid. The continents in one rotation are not really moving relative to each other over the millennia or millions of years. They do move, but they're kind of fixed to each other, so it's the same rotation relative to each other. That's what I just said. That wouldn't be the case for the Sun or for the gas planets, but for the Earth and the other solid rocky planets, it's definitely the case. So we're going to come up with something here, and I can just tell you what the answer is on this one. So that's 1/3 of that tangential speed that you're supposed to calculate. And I'm just going to take my own here that I calculated earlier and divide that by the 7.3 10 to negative 5, and I come up with 2.12. What do we have here? 2 or 3 significant figures? Oh, 3 significant figures. 2.13 times 10 to the 6 meters. I remember in the problem it was stated that the other radius was 6.38, so that's actually 1/3. That's really the only thing that changed. And so the follow-up from that one is now to figure out, well, at what latitude is that, so that theta here, and I'm going to make a little triangle here. This is the radius that they want us to figure out in part B. And then here we have that angle theta. And we know what the hypotenuse is. The hypotenuse, this one here, is the same as the radius, because we're having a circular Earth. So here we have the hypotenuse. We're supposed to figure out what the adjacent is, RB. And adjacent, of course, goes with the cosine. So the cosine of that angle, that latitude they're looking for, equals the radius B divided by the radius of the Earth, or at Ecuador. So maybe I write RE here for Ecuador and the Earth, and therefore we come up with theta equals the inverse cosine of those two numbers, RB over RE. And because they're asking for a latitude which is not given in radians, I would put the calculator in degree mode. In fact, it comes out to a latitude that is kind of northern Alaska. Doesn't show quite well on the map here. It looks like more like southern Europe, but as I said, northern Alaska would be the correct result. By the way, I'm not going to write this down here for the centripetal acceleration, so I'm just going to tell you that if we calculate the centripetal acceleration at the equator for Ecuador, we would have centripetal acceleration equals radius times omega squared, and we would have everything given, and I come up with 0.04 meters per second squared, and it's a centripetal acceleration that is being supplied partially by gravity, and then the rest of gravity is really pulling the person down, and because of those 0.03, I believe I said, meters per second squared, that's the reason why the gravity, so to say, is a little bit less at the equator.